So to start off, we're gonna do a little 10-minute getting started. So we'll go to about 8:10. So this will be pretty quick just to let people filter in as they come in. You heard from Alex and Dylan yesterday. Did a walkthrough of quite a few things. You're gonna hear from me today. We're gonna go over kind of cloud computing in general. About a half hour just talking about cloud computing, what that looks like, and especially from the viewpoint of a scientist coming to the cloud for maybe the first time. We're going to talk about how you would go about scaling your algorithm with tools like Hype. We'll take a little bit of a break, and then we'll do some algorithm development best practices. So the scaling your algorithm part will be a live coding thing. We're actually going to wrap in the notebook that we worked on yesterday in a Docker container and go through how we would make that kind of cloud ready. After the break, we'll come back and we'll do a more kind of open exploratory coding where we'll just kind of walk through the notebook and some maybe things we could do better and why we've chosen to do things certain ways. I would expect that to be very open QA space. So feel free to raise hands and dump questions into chat during that entire time. And then we'll go kind of back through some cloud best practices and gotchas, and then there'll be a period for just open QA about everything at the very end. So a little bit about me. I think it's important to kind of set the stage of the viewpoint that I'm going to be taking through this. I have a PhD in computational glaciology. I was doing multi-scale ice crystalline microstructure as part of my thesis. That led to a postdoc and staff scientist position at Oak Ridge National Laboratory, where I was using the top supercomputer in the world at the time, and currently still the top supercomputer, as well as I think I had access to 13 supercomputers at the most at one point, doing Earth system modeling, so large scale, heavy computational workflows, and also focusing on verification and validation. So a lot of matching observations to models. That led to this research software engineer initially and staff scientist position here at ASF. Our mission here is to make remote sensing data accessible. So I joined the tools team, which is a team that builds kind of general tools and services for the user community. The on-demand processing platform is primarily what the tools team works on. I led, along with Andrew Johnston here, the ground-up redesign of Hype. It started as a student project and was in beta for a long time, got really popular. So we rebuilt it to be a kind of a NASA enterprise quality application. So I have both a foot in the software and science worlds, and I spent a lot of time thinking about science workflows. How do we generate products? How do we prototype them, scale them, analyze them, and kind of go through this prototype to production life cycle. So what I'm going to present here is very much through the lens of a scientist trying to scale a workflow, not as a software engineering trying to build services. And that's an important distinction, especially later when we talk about Docker and Kubernetes and things like that. As a software engineer, you will have training in a lot of these technologies, and you will understand and use them as your primary technology stack. As a scientist, you're typically not trained in Docker, even let alone Kubernetes or anything bigger. So that's the lens that we'll be talking about through here. So as a reminder, we're recording the videos. They'll be posted to the NASA Earth Data YouTube channel. It's going to be a live coding demo that goes poorly sometimes, so bear with me. And I've tried to reserve lots of time for questions. So we'll give it, I think I still see people coming in, so I'll give it just another minute and then we'll start here. All right, so we always hear a lot about cloud versus on-prem, and do you want to run your workflows on cloud, or do you want to do things on-prem? And usually in the science community, we have a different meaning of that than what you hear typically in industry. So when you Google those, what you end up is this discussion in industry, which is in the cloud, you own nothing, you're paying for usage, and what you have to then invest in as a company is training and DevOps personnel to help with the cloud, the migration, the tooling to use the cloud, et cetera, versus on-prem where you own everything. You buy the servers, the software that goes on them, then pay for the admin personnel. And so you're really paying for capability. Well, once you hit your capability limit, you're either buying new software or using the cloud or something. So most organizations are actually hybrid in the end. They use the cloud where it fits. They pay for server capacity when they want to like finely tune or optimize better than they can get out of the cloud. When we're talking about kind of academic or science research in general, whether it's in industry or in a university kind of space, we're really talking about kind of a workspace where you're used to working on your laptop. You might have a bunch of hard disks that you've that you've got under your desk because you've got data from past field campaigns or a bunch of remote sensing observations from different papers previously. Thumbsticks littering your office. Maybe if you're fancy in one of your grants, you have a network attached file system kind of under a desk somewhere, probably a graduate student's desk. And so you're often copying data back and forth. Everything's living locally and on disks. As you get farther along or more advanced labs, you might have a server that gives you higher capacity that you SSH into, copy data back and forth from, et cetera. So a lot of your primary tools are copying and SSHing and interacting with stuff. And that sort of pattern matches what you see at universities as research computing services get bigger and more services added onto them. You might have access to a distributed computing cluster where there's a bunch of different machines that you can have access to, but they're all networked together and can tackle larger problems. Or you may be at a university where you have a high performance computing center or a supercomputer where it's just a nice big giant computer with really big fat nodes and everything's networked together, and you can process these big jobs. And so when you're talking distributed computing, you're thinking mini computers networks together. If you think of a job as the general term, they're split out into tasks that are then distributed off to these different computing nodes. So that each computer is a node, the node takes on tasks. Anytime that a task needs to communicate, it happens over just the basic HTTP network. And in distributed computing, the computers and the nodes are pretty limited usually. They're like a bunch of laptops slapped together, or maybe a bunch of servers slapped together. This is really powerful for certain problems that are small, but you want to do a lot of. So there's some really big, nice infrastructure built around this idea. The Open Science Pool is kind of a global science pool, largely funded out of the US, that provides a massive distributed computing cluster that you can access for free. And there's also the European grid infrastructure. But you've got to be able to fit kind of your work onto effectively a laptop size system or effectively break your work up into those type systems. So the resource requirements here that I've listed are for the Open Science Pool. Whereas when you're talking about high performance computing or supercomputing, you've got effectively one giant computer. It is comprised of many nodes, but those nodes are high performance nodes. So they're hooked together over specialized high performance networks using InfiniBand networks, mounted Lustre file systems that's shared that are super high performance. And so you run a job on a selection of nodes, you effectively get yourself a subset of that computer for an amount of time. And when you're in this application, you're using specialized system-specific libraries. Often it's going to look like an MPI run in the end, and you're using, it's an Intel system, Intel's compilers that they may have even tuned specifically for this machine. Individual nodes are beefy. So if you're talking NASA Pleiades, for example, It'll have 28 CPU cores, 125 gigs of RAM, and 2 terabytes of disk available to you. So significantly larger processing on an individual node level. So NASA Pleiades, which many of you may have access to, is the 155 of the top 500 supercomputers in the world. So that's 10,000 nodes, 22,000 CPU cores, effectively a petabyte of RAM, and a 90 petabyte cluster file system. When you come into the cloud, though, all of those normal patterns, copy, SSH, all of that kind of stuff, become a bit different. So scaling from university researcher to server under the desk to an HPC center is a more straightforward path, though by the time you get to HPC, you started to dig into some very specialized tools and knowledge. So when you think about cloud is generally thought of as like a near infinite well of computing capacity and services built around that. So you don't really have a machine that you're trying to match your compute to. You have a system you're trying to build to match to your compute. So you build your own infrastructure to suit your needs. You pay as you go. So everything you do costs money, and in the end, you get billed for it. And then everything is API driven. There's not a whole lot of like direct access to things unless you specifically set that up yourself. So what you're doing is often asking for a computer. It can be just an individual EC2 instance, or it can be a supercomputer using a AWS parallel cluster. So you can do all of kind of the styles of computing in the cloud. And really the model is more, you can do whatever you want if you can build it. So when you're in the academic space thinking, do I want to use an HPC center or the commercial cloud or maybe one of these federated grids of computing, the question often comes down to like what style of computing that I'm doing in an ideal world. So when you think about styles of computing, there's a couple like things to think about. Embarrassing parallel are really easy kind of ways to think about processing. It's just one task does another, does another, does another, and then everything else is independent. So a lot of remote sensing applications actually look embarrassingly parallel. I take an input scene, I do a thing. I take a different input scene, do maybe the same workflow, but it's independent of the other one. Whereas in machine learning kind of applications, you see a lot of things like MapReduce, for example, where the nodes might be independent for a little bit, but then they have full network communication they need to do. And then that branches out and goes into another set of independent tasks that then communicate again. So if we want to put these tasks on computers, we've got a computer this size that can take 2 of these embarrassing parallel ones, pretty easy, run it along, great, easy to distribute. If we try to do that in a MapReduce workflow, all of a sudden we have cross-computer communication that needs to happen and a decision where certain tasks live. So at this point, we need a task manager to handle it, or we say, forget it, I just use a bigger computer. And we kind of pack jobs in that setup. In the embarrassing parallel sets, it's easier actually to use smaller computers. You can match the computer to the largest task in your task chain. So right here, we can actually use 4 computers, distribute out in parallel even better. And computers I'm using here is just a general sense. It could be CPUs or anything. The idea here is just once you have to cross node or computer boundaries, you have communication. Communication is either expensive in terms of time or in terms of resources needed to make it happen. And when you're talking HPC systems, the task graphs look insane. And so there's a lot going on, a lot of communication. And that's really the defining characteristic of HPC, is that you need these fully interconnected nodes that can all talk to each other over these really fast networks and all write to the same file system really quickly. When we talk about something else, instead of high performance computing, we're talking about high throughput computing. We're really talking about running a large number of embarrassingly parallel tasks. So I have a supercomputing model that I want to run, but I want to do a parameter study. So I just want to tweak these 100 parameters 50 times each. So now I have to run just an absolute crazy amount of jobs, but they're all completely independent. I just fire them off into the queue and wait for them to finish, sort of thing. So that's high throughput computing. And high throughput computing has a very different set of tools that are kind of built on top of it. So once you get into high throughput computing, you're really thinking about running workflows and running multiple workflows instead of running individual like notebooks or models or that kind of things. So Hype, which we'll talk about in the end, is really geared towards this high throughput computing kind of space. Once you've kind of locked in the computing area you need, whether it's a laptop sized machine or all the way up to an HPC sized machine. So back to our question, do I use HPC Center or the commercial cloud? If you're at an HPC center, you've got a predefined computing platform. It is administered to maximize utilization. So the success of an HPC center is tied directly to how many bits they process. So they want 100% utilization 100% of the time. That is their goal. So often queues are designed to prioritize really big jobs that use lots of nodes. And then they pack in smaller requests around them. So if you have high throughput computing where you only need one node or two, you actually can get deprioritized. And so you have to figure out how to adjust your queuing strategy to meet the administration of the machine because you're competing with other users. In an HPC center, you'll also need to move your data. All the input data needs to be on the Lustre file system to take advantage of the network interconnects and all of this kind of stuff. And the output data can be hard to share. The HPC centers often deal with classified or highly sensitive data. And that means that there's a lot of access control mechanisms around data on and off of the machine. You can't just share an HTTP link to somebody outside of the HPC center to your data typically without doing extra work to make that happen. So HPC centers and these large distributed clusters are ideal for jobs that need network and disk communication. And the key thing here really is when moving data to the compute is easier than moving the compute to the data. Commercial cloud is sort of the other end of the spectrum. It's an undefined computing platform. You have to build it yourself. But you can use managed services, and I'm going to talk about managed services a bit later. They help you with the building. You don't really compete with other users, except in cases where you explicitly try to, which is in the spot market. So when you fire an instance on AWS, you can fire an on-demand instance, and you just get it, and it lives as long as you're willing to pay for it. Or you can fire a spot instance that's 1/3 the cost typically, the same instance type, but it can be interrupted when somebody needs it. When somebody fires and wants to fire an on-demand, it'll shut yours down and take yours for them. So you can leverage cost savings by competing, but you don't have to. Data movement in the cloud is typically pretty easy as long as you can access the data via HTTP. It's always going to be better if it's in the same region of the same cloud that you're in. So in AWS, most of NASA's data is going to be in US West 2. So if you're computing in US West 2, you'll get crazy fast network connections to that data and potentially less charges to your account because of that. They'll charge you for moving data, or they'll charge somebody for moving data across regions or out of the cloud. And output data is very easy to share. If it's an S3 bucket, everybody can just get an HTTPS link for it. If you make it public or requester pays, it's really easy to find and use. And so the cloud's really ideal for doing lots of something, especially little things. You can be very cost effective in the cloud if it's a bunch of little things you're trying to do. It's most effective to use the cloud when moving the compute is easier than the data. So it's a lot easier to move my compute algorithm next to the data, process the data with a fast network connection than it is to copy all the data down to an HPC center and process it there. So with NISAR, we're talking about potentially ingesting up to 50 petabytes of data a year. This is going to be an unprecedented amount of data volume. So ASF historically in like 2014 had 1 petabyte of SAR remote sensing data. By this year, we're up to 22 plus petabytes of data. Come NISAR in just the next few years, we're going to be up to hundreds of petabytes of data to access and process. So if you remember from our NASA Pleiades, you could fit the entire SAR archive on the 90 petabyte file system in Lustre and process it if you could get permission from the system admins. There's actually space for that. At NISAR levels, you're blowing away every supercomputer's file system. Like they do not have capacity for this much data. So the amount of data to move is going to be going to take significantly more orchestration. It's not going to be available typically at your HPC center for you directly. If it is, it's going to be on tape storage, not on fast access storage. So either way, you're going to have to do a bunch of data wrangling to get to it and access it. So we're looking at the future of a lot of, not all, but a lot of analyses with these large remote sensing observations is going to be effectively cloud-based. So NASA is all in on AWS. Almost all of the data is either already in AWS S3 or actively migrating to S3. I think it's the end of this year, end of 2025. All data is supposed to be live and actively distributed from S3. So new missions are also going to provide this unprecedented volume of data. I would expect Roselle, when it launches from ESA, to have this same issue. NISAR Next is going to be, Landsat Next is also going to be significantly higher resolution and a lot more data. So we're getting to a regime when you're doing large scale remote sensing computation. So global kind of scale, especially global and temporal full scale computing, it's going to be way easier to move the compute to the data than vice versa, and potentially impossible to do it the other way around. So all that said, external HTTP access, moving the data out of the cloud will remain free from NASA, and it'll be available and easy, but in region access where you're in the cloud right next to the data is where you're really going to be able to do really cool stuff, where you're going to really accelerate your science. So I said this a little bit already, but many remote sensing applications are ideally suited to this cloud-based workflow because we can decompose them into embarrassingly parallel workflows. So this is actually a really good fit for Earth observations. If you can break it down on a scene-by-scene basis, it's really easy, or scene pairs basis, to break out computation, distribute it out easily, and then come back together. It is worth noting cloud is hard. Like, I think that's something that most everybody experiences, especially if you're coming from a traditional sciences background. Almost all of the technologies are new and unfamiliar. We don't typically get taught them. Might be changing in courses now, but if you're older like I am, none of the cloud was even a thought when you went through grad school. Budgeting and paying for clouds is a completely new model. You actually typically have to write the cloud charges directly into the grant, and instead of applying for a secondary allocation from an HPC center directly, if you make a mistake and you use a lot of compute that you didn't realize you used, you're still on the hook to pay for it. So, and this kind of situation happens pretty regularly. When you're new to AWS, you might accidentally spend $50,000 and not realize it. But it also happens to people that are very experienced at AWS. I myself have recently accidentally spent a few $1,000s I didn't mean to by resubmitting processing requests without realizing it. Because you're building everything, you now have to control all of your permissions and access. So when you're in AWS, access controls are managed by AWS externally with something called IAM, Identity and Access Management. What that means is that when you get a resource, you get the resource. So like if you fire an EC2 instance, you have admin sudo access to it. So AWS protects itself and its accounts, but it does not protect you from yourself. So you can go ahead and do whatever you want, but you can do whatever you want. So you have to be actually thinking about permissions and access quite a bit. And then your data and computing patterns change. You're going to be always accessing via HTTP access. You're going to be hitting APIs. You're going to be doing a lot of these things that you wouldn't necessarily be doing at a local file system level or on your laptop. And so we're going to kind of dive a little bit into Docker. Docker is probably the standard way to move your compute somewhere else at this point. So container images, Docker container images, or whatever the open container image protocol is, are open portable packages of your code and dependencies. They are a good way to move your compute. You package up your code, all the dependencies that's needed into effectively a mini file system, and you can then run it on a different machine, and it should be exactly reproducible. You get the same results out. And from the comments I see, I will talk about budgeting a bit more towards the end as well. And yeah, you can spend days on budgeting. So container images work best for distributed computing, and I'm specifically talking about Docker here. Distributing computing and going to the cloud. The fun of Docker is that it gives you admin privileges, and it's really hard to ensure that the container running doesn't have the capability of assuming root or admin privileges. So most HPC systems kibosh Docker. And instead you use a technology called Apptainer, which was formerly known as Singularity. This doesn't do privilege escalation the same way that Docker does. It allows you to run HPC systems, and they can use, Apptainer can run Docker images using its container running engine. So you can still build Docker images, but you're going to run them in HPC systems with Apptainer. And Apptainer has a lot of hooks and tools built into it to make it easier to use system libraries. So the specialized MPI for that system, the specialized Intel compiler, and those kind of things. When you think about what is happening on the cloud, basically everything runs on a container in the cloud, and most of the things that you try to do in the cloud that don't run on a container are actually running on the container in the back end. You just didn't have to deal with the container. I think coming from containers from a non-CS perspective or a non-software engineering background, you can fairly say containers are hard. The initial create a container, writing the Docker files, not so bad. It just looks like writing a shell script. But then getting data in and out of the container is a whole world of what. User privileges are very confusing, and you have to rebuild the container if you did them wrong. Networking is a whole level of pain that you should avoid as much as you can. And the Docker daemon runs the actual container when you're actually running it. It's running as root, so there's a whole bunch of stuff that come with that. So containers are pretty easy when you stick to the basics, but there's a lot of edge cases that can really bite you. Alternatives to containers are, for kind of science, Coiled is a kind of commercial company that effectively handles the container part for you. It syncs your environment, your Python environment or your Conda environment into the cloud for you. It assumes you're just working in that environment. it does that by running its own containers and copying your environment into its containers and running it for you. But you don't have to think about them that way. It's just, here's my environment, run it in the cloud for me. And so this is really powerful if you just want to run a function in the cloud, or maybe a small bit of Python code. AMIs, virtual machines, are other ways to do this kind of virtualization, containerization. They work at a lower level than containers do and can be a lot more complicated and are harder to ship and move around. And a lot of things have moved from those to containers. But that AMI, with VMs versus containers, is a whole other lecture. Or you can just SSH into stuff and manually do it yourself. So my recommendations with Docker, so this is from a very science perspective, is keep it simple. When you're doing science workflows, a Docker run command is probably all you need. All you want to do is type Docker run my workflow and the parameters it needs, and it runs the workflow and spits out the output products that you want. So whether it's modeling, I take my input data, run my simulation, it out dumps the simulation files, those are my output products, puts them somewhere I can get to and look at later. Or remote sensing, it takes my 2 input scenes, run my interferogram processing on it, dumps out my interferograms and covariance map and those kind of things for me to use later. If you can avoid everything else besides just the simple Docker run, try to do that first. So aim for ease of use first. And we'll get into that directly here in code in just a few minutes. Portability and optimization can conflict. So Docker's really, it's possible to build a workflow that's completely portable. You can run it in the cloud, you can run it on the HPC center, you can run it on your local machine. It might not be optimized for any of those in that case. I would caution that you really don't want to optimize prematurely typically. Get something working, get something simple working, and then go from there. And I'm going to recommend generally, if you need a cluster, let someone else run it. So if you've got a bunch of containers that you need to run and they're not simply parallel, they need to talk to each other, then all of a sudden you need a cluster. And if you're in a small research setting or a typical research setting where you don't have access to just software engineers to help you, or funding to pay those software engineers to help you, you're not going to want to run a cluster. So that's when you might want to look at AWS managed services. So AWS Batched is a fantastic way to run containers in the simply parallel set. It's just, here's my Docker run command, run it on this instance. Here's my Docker run command, run it on this instance. And it just handles all of the scaling and downscaling for you. And as long as your Docker containers write your output products to S3, then you're good to go. And then there's software as a service providers that will do all of these things for you as well. They might be the cloud themselves via managed services, or they might be a third party. So when you are in the cloud and you've decided you're actually going to build stuff and not pay someone to build stuff for you, there's a bunch of stuff that you'll have to do. You're going to have to build your resources. You're going to have to compose them, put them together, and make them talk to each other and give them all the right permissions. So you're going to really, really want to use infrastructure as code. So infrastructure as code is typically YAML files that manage and provision the resources kind of through a machine readable and ideally human readable definition file. So in AWS, you're going to use CloudFormation. That's a JSON or YAML file. I have an example of CloudFormation YAML below. I have an EC2 instance resource I want. I'm going to launch a T2 micro size instance using this AMI image ID. And if I could run this CloudFormation deploy, you can see this image pops up and running, and then I can connect to it and all of this stuff. And then if I want to tear it down, I can just tear down that CloudFormation stack with a single command line parameter. And all of that all happens for you. It's very easy to check or have somebody look over your infrastructure, to check on your infrastructure, see why things changed, make updates explicitly, have your updates previewed, those kind of things. The AWS CDK is a really cool wrapper on top of CloudFormation effectively. It allows you to dynamically generate it in TypeScript or JavaScript, Python, Java, CNET, Go. And so this lets you kind of work in a language you're familiar with, using a lot of the tools. They have a proper programming language to build your templates. You don't actually see the templates in the end without work. But it gives you a way to kind of build your infrastructure dynamically in a language you're familiar with. Terraform's another option. It's really popular. A lot of places go towards Terraform, especially if you have cross-cloud resources to manage, because Terraform is kind of an external infrastructure provider. And so you can do Azure, Google Cloud, Amazon, and a bunch of other providers with Terraform, like Oracle, those kind of things. And then the nice thing is, once you've got the infrastructure as code, you can check it into your Git. You can have it live right next to your actual code you're trying to run. It's very easy to see everything together in one kind of context. And then you can hook it up to CI/CD infrastructure. So what your CI/CD is continuous integration, continuous deployment. It's a set of practices that help you deliver code changes kind of more frequently and more reliably. It automates kind of testing, building, releasing, deploying all of the things that you need to do once you want the code to go into the world. And so when you're kind of a science team and you're small, especially, I think leaning into infrastructure as code, continuous integration is a really good idea. It does require a learning curve, but what it allows you to do is use tools, not developer time. And so all of these things that you could do manually and may want to do manually sometimes can be automated, and you can provide really easy, nice review gates and checks. So we'll go through some of this live in a few minutes. And there's many providers of these kind of continuous integration software. The most popular ones are GitHub Actions, GitLab CI, Circle CI, Jenkins. There's a bajillion of them. So generally what it looks like is you have your source code. When you push updates to the code, it triggers a bunch of these actions to run. So this is the GitHub view of the world. That action could be, for example, build a container image, push it to the container registry on GitHub. And then once that's done, deploy your code, deploy your infrastructure from the infrastructure code using the container images to AWS. So all you have to do is git push, or ideally git merge a pull request so that it's been reviewed and checked by somebody. And then it can deploy after all the tests pass and everything's ready to go.